Hello, my friends. Good morning, good afternoon, good evening, whatever time of day you are deciding to watch these videos. For this week, we are going to be working through the process of science. So this is module 1.2 in your book. So what we're going to do, or what these next few videos are going to look at, are basically what is science, the scientific method, and then lastly, some analysis and conclusions and things like that we can make throughout our time together here as scientists. So I'm excited to have us walk through these ideas together. And by the way, I will post these slides as well, so you will have access to this information. So, the process of science. So the first thing to consider, of course, is what is science? So the term science literally means to know. That is like the basic definition of science, is to know. So as scientists, what we do is we gain knowledge through experience. We experience things in our everyday lives. It doesn't just have to be scientifically related, but you come to school every day, you go to work, you take care of a friend or family member, you read a book, you do a puzzle, you, knit or crochet. Anything that you do in your life is through experience. If you've ever had to complete a job description or, put on your resume, your experience, right? So, but with science, this is the process of science is gaining a better knowledge and understanding of the world and planet around us through experiences that we can create. Science is also an accumulated body of knowledge of the physical or material world through observation or experimentation. So oftentimes what scientists do is we observe, see what happens, and then we can make conclusions based on our observations. And the best way that we can do that is create experiments in a lab, and then within that lab and within those experiments, can we replicate what we observed? And that's really also, by the way, that's a huge thing that we need to do with climate models. So we're going to weave climate change all throughout the semester, but the main idea with climate models is we build a model, build a computer simulation, for lack of a better word, and we then run it backwards in time, especially for the period of time that we have observations for. Like, for example, we have temperature observations, global temperature observations until back to like 1800s or late 1800s, So if we run our climate model to that time and that climate model replicates what we observed, then we can say that that climate model is working pretty well. Granted, with climate models, we left to go like thousands of years beyond there, but that's just, hopefully you're understanding what I'm trying to put down there. But we often try and do experiments. Like maybe when you think of science, you think of chemists or biologists in this lab with their lab goggles on and working with these vials and beakers and mixing all this stuff together. That is a form of science, of course. But there's other forms of science as well, like taking things out into the fields, like meteorological instruments, and setting them up and just being like, okay, take stuff now for us. And then we'll take that information back, run it through computers, do analysis on it, and that can help us gain knowledge of parts of the physical world. Pretty cool. Lastly here, facts or principles gained by systematic study. So we know things like Newton's laws of motion, and that's like something what's the first law? It's like an object in motion will stay in motion at the same rate of speed in a straight line forever and ever, amen, until an opposing force acts on it, right? So that is a sort of principle or a law. Even the theory of gravity, systematic study, right? So that's a big thing to consider. Next up, with science, we have to make a few assumptions. In meteorology in particular, we make a lot of assumptions. within our models and within our knowledge of our atmosphere. But the thing that we need to consider is that there is order to the universe. That's a really big assumption that we make. Some folks can argue against that. If you've ever heard of like the chaos theory, for example, or like if a butterfly flaps its wings in Japan, that can cause a tsunami in the Atlantic Ocean. You know, there are obviously some differences there, but it's pretty interesting. But the reason that we perceive and make this assumption that there is order in the universe is because the human mind can actually physically comprehend this order. And within kind of the smaller aspects of science, as opposed to like big universe, Big Bang theory sort of ideas, the idea with science is if we have conditions that are the same, then the results of any study will then be the same. Repeatability is gigantic in science. It is like one of the number one things that we need to consider as scientists. And when we go through the peer review process, when we go to conferences and things like that and support and try to defend our studies, we have to make sure things are repeatable. That someone elsewhere can take our methods, take our data sets, and repeat the experiment. And if they come up with the same results, beautiful. That means that they are aligning. That means that we're not the only ones coming up with that conclusion. And that is a massive, massive thing in science. Next up, move my head here. Which of the following statements can be tested scientifically? So this is a pretty interesting little exercise that we can do. So I have several bullet points here, and we're going to work through each of them individually. So this first bullet point, most of the energy coming from the sun is in the form of visible light. Can we test this idea? Yes, we can. We can take an instrument, we can measure what's coming out of the sun, and we can use a curved line to see the wavelengths that's coming out of the sun, that the sun is always constantly emitting. And we can determine on the electromagnetic spectrum if what is coming out is invisible light. Is it only visible light? No, it's also emitting ultraviolet rays and infrared radiation, but a majority of what's coming out of the sun is visible light. We got it. Awesome. Shakespeare wrote great plays. Can we scientifically prove that? Unfortunately, with that bullet point, that is an opinion, right? Some folks may love Shakespeare, some folks may not like Shakespeare, and some of us may not think that his plays were great. So that is an opinion. That is something that we cannot scientifically test. Next one, can we test that the Earth is about 4.6 billion years old? Yes, many scientists all over the world have done various studies on the age of the Earth via different methods, radiometric dating, and things like that, which have all come to the same conclusion that the Earth is about 4.6 billion years old. Next one, are unicorns real? Well, we can test that we've never seen them. Does it mean that they've ever been around? Not necessarily, but that is not something that we can scientifically test on this bullet point being true. Second to last one here, diamonds are more beautiful than rubies. That again is an opinion, right? So diamonds being more beautiful than rubies, I'm personally not a diamonds gal. I personally prefer stones. So would I say that they're more beautiful than rubies? No, but some folks really love diamonds for whatever reason. And so, they may say that diamonds are more beautiful than rubies. But again, that can't be scientifically proven. Can we test whether or not diamonds are harder than steel? Yes, we can do that. We can literally take different materials and scratch them with either diamonds or steel or try to break them down with the same amount of pressure. Then we can say that yes, diamonds are harder than steel. So these are things that we can test scientifically. The ones crossed out in the red are ones we cannot technically test scientifically. So these are always things to keep in mind when you're going through potential scientific questions. Last thing is that all good scientists exhibit these several traits. Curiosity. Every single scientist that I've met has always been extraordinarily curious, almost to a fault sometimes. All good scientists are honest. Being honest with themselves, being honest with their colleagues, being honest in their writing, in their work, that makes a good scientist. Having an open mind. This part is also huge. And in a sense, in like a maybe side bullet point with that one, having a growth mindset, I think, is also a very big deal. Sometimes we're wrong. Sometimes science further down the line can disprove a belief that we've held for a long time. That's okay. And having an open mind to seeing what the new evidence is telling us, that is extraordinarily important. Willingness to be wrong and to make mistakes. This one's also huge. It's sometimes really hard as a human to say, oh my gosh, I made a mistake. I'm so wrong. I'm so sorry. Let me fix that. And it's a good scientist will recognize, or a good human really also will recognize, hey, I was wrong. I made a mistake. I'm human. I apologize. Let's move on. That's a good thing to do as well. Asking good questions. And really most questions are good questions, I would argue. But trying to figure out why someone came up with the conclusion that they did or anything like that is a part of asking good questions. And then lastly, being skeptical. Having skepticism of whatever results are thrown at you. Looking at who funded who and what funded what. Where did the interest of this research come from? Why does this particular body, this particular company or government, whatever, why do they want to have this answer and why are they producing the answer they're producing? It's always really good to be skeptical to a point. So those are things, that's what science is. That's what makes a really good scientist. So I hope that you take that to heart and use that within the rest of our journey this semester. Thank you so much for watching.